Hey folks, welcome to Digimento Education. So this is Electronic Devices and Circuits lecture 8. Hopefully you must have gone through all the lectures that I have covered, and please subscribe to our channel so that you never miss out any update from us, and you should be so that you are available with all the videos that we upload on YouTube. So let's begin with this lecture. So as discussed in the last lecture, we are going to we will be discussing some questions related to the previous topics that we covered. So let's have a look. So this is the first question. The question says a sample of germanium is doped to an extent of 10 to the power 14 donor atoms per centimeter cube and 5 into 10 to the power 13 acceptor atoms per centimeter cube. Okay, so it is important to note down that the semiconductor is doped with both donor and acceptor impurities. At 300 Kelvin, the resistivity of intrinsic semiconductor germanium is 60 ohm centimeter. Be careful with the units, everything is given into centimeters. Okay, if the applied electric field intensity is 2 volts per centimeter, find the total conduction current density, assuming Ni is equals to 2.5 10 per 13 per centimeter cube and mu p by mu n is equal to half. Okay, so let's solve this question. So what are the information that we are available with? So we are available with the Nd, which is 10 to the power 14 per centimeter cube, okay, and Na, which is 5 into 10 to the power 13 per centimeter cube, which is basically, if you just write in terms in the same units, is 0.5 into 10 to the power 14 per centimeter cube. Okay, now intrinsic resistivity rho I is given to us as 60 ohm centimeter, which is at 300 Kelvin, and magnitude of electric field intensity is 2 volt per centimeter. So what are we asked to find out? Find the total conduction current density. We need to find out the conduction current density. Now rho I is given to us, so Ni is also given to us, mu p by mu n is given to us. Now from here we can judge that Nd is greater than Na. So we can say that since Nd is greater than Na, so it is n-type compensated. It is n-type compensated. Okay, now we know rho I, so 1 upon which is Niq mu n plus mu p. We know this partition for the intrinsic semiconductor, so this will be equal to, and mu p by mu n is known to us, so this can basically reduce to, so if we just plug mu p as mu n as 2 mu p, so we can get Niq 2 mu p, sorry 3 mu p, because it's mu p plus 2 mu p. Okay, understood? So then we can find out the value of mu p is 1 upon rho I Ni into 3q, and when you solve, you get the result as, by plugging the values of rho I, Ni and q, you get the value as 1388, so you get the value as 1388 centimeters square per volt second. Okay, and we can find out the value of mu n, which is 2 mu p. This is basically equal to 2776 centimeter square per volt second. Understood? So now we have got the values of mu p and mu n. Now we require the concentration of electrons and the holes. Okay, now if we just have a look at the value of Nd minus Na, so what was the value of Nd? Nd is equal to 10 to the power 14, so 1 minus 0.5, so if we can get 0.5 into 10 to the power 0.5 into 10 to the power 14. Okay, 0.5 into 10 to the power 14 per centimeter cube. And what is Ni? Is 2.5 into 10 to the power 13 per centimeter cube. Okay, now since Nd minus Na is not greater than 10 times of Ni, because 10 times of Ni is 2.5 into 10 to the power 14 per centimeter cube, and Ni is comparable to Nd minus Na, since Nd minus Na is not greater than 10 times of Ni, so we have to use the equation that we derived. So since it is n-type compensated, we can find out the electron concentration as Nd minus Na by 2 plus square root of Nd minus Na by 2 whole square plus Ni square. Okay, now electron concentration, this is 0.5 into 10 to the power 14 by 2. Remember that you need to take an extra care while considering the units. Okay, this is 0.25 into 10 to the power 14 by 2 whole square plus 2.5 into 10 to the power 13 whole square. Understood? So electron concentration, when you solve it, you get 6.03 into 10 to the power 13 per centimeter cube. So this is the electron concentration, and since it is n-type semiconductor, we can find out the whole concentration as Ni square by Nn. So this is 2.5 into 10 to the power 13 square divided by, it is 6.03 into 10 to the power 13. We get the value as, when you solve it, you get 1.03 into 10 to the power 13 per centimeter cube. Now the conductivity, now current density, now current density. So in this case, the current density is basically the drift current density. There is no diffusion current density because nothing is mentioned about diffusion in the question. So by default, you are going to consider drift current density. Okay, so which is basically Nn Q mu n into electric field intensity plus Pn Q mu p into electric field intensity. So from here you can say that Nn is 2 into 1.6 into 10 power minus 19. We can take E and Q out, and 6.03 into 10 to the power 13 into 2776 plus 1388 into 1.03 into 10 to the power 13. Okay, we get 3.2 into 10 to the power, we solve, minus 19 is 16739.28 into 10 to the power 13 plus 1429.64 into 10 to the power 13. We solve it, you get J drift, which is a required thing to find out, 0.058 ampere per centimeter square. So this is the answer to this question. You cannot expect this expect the question of this length in the MCQ type questions, but you can expect it to be asked in the IES mains examination or NAT type question in the gate examination, numerical aptitude. It can be NAT question, NAT, or IES mains. Okay, you cannot expect this type of question asked in the MCQ. So be it's just for clearing your concepts. Okay, let's have a look at the next question. So this is the next question. So it says at 300 Kelvin the band gap and the intrinsic carrier concentration of gallium arsenide is 1.42 electron volt. You should remember this particular value, okay, for gallium arsenide, and 10 to the power 6 per centimeters cube respectively. In order to generate EHP, which electron hole pairs in gallium arsenide, which one of the following wavelength ranges of incident radiation is most suitable? Given these values, Planck's constant, C, and Q. So the other options going to, let's find out which option correctly matches the requirement. Okay, so we know, as we already studied in the last lecture, that we can find the critical wavelength. Okay, 1.24. Okay, it's 1.24 upon EG micrometer. Okay, so 1.24 upon EG micrometer. So lambda c is 1.24 upon 1.42, and this value comes out to be 0.838732. Okay, 8732 micrometer, which falls in what range? It falls in this range. So answer to this question will be equal to this. This question was asked in GATE 2014. Okay, understood very well. Okay, so let's have a look at the next question. Okay, so this is the next question. What does it say? Let's have a look. The longest wavelength that can be absorbed by silicon, which has band gap of 1.12 electron volts, is 1.1 micrometer. If the longest wavelength that can be absorbed by another material is 0.87 micrometer, then the band gap of this material is what electron volt? Since we are now given the values, Eg1 as 1.12 electron volt and lambda c1 as 1.1 micrometer, we need to find out Eg2 when lambda c2 given to us is 0.87 micrometer. So we use the relationship that Eg is inversely proportional to lambda c. Okay, so we can say that Eg2 by Eg1 is lambda c1 upon lambda c2. Okay, by plugging in the values, we can get Eg2 upon Eg1 is 1.12, lambda c1 is 1.1 upon 0.87. So when you solve, you get Eg2 as 1.41 electron volt. So this must be the answer to this question. Understood? So it's better that you should write all the values that are given to you in the question, so that it basically minimizes the complexity of understanding the question very well, so that you are available with all necessary information, and you can use your own notations like lambda c1 and lambda c2, so that it is more legible and more credible to you to understand very well. Okay, now we are starting with the new topic that we are going to discuss in greater details. So the topic that we are starting today is minimum conductivity of a semiconductor. So it's minimum conductivity of a semiconductor. Okay, we are now trying to find out each and every important behind this concept. Okay, what is the minimum conductivity of a semiconductor? When is the temperature? At what temperature does a semiconductor exhibit minimum conductivity? So we know for an extrinsic semiconductor, we know the conductivity formula. Okay, sigma is nq mu n plus p q mu p mho per centimeter. Okay, the units are tacit, so I'm not writing those thing again. Okay, now let's apply the mass action law. P is equal to Ni square by N. We know this thing for an extrinsic semiconductor. By default, we are considering N-type semiconductor. Okay, so substitute this is basically the equation 1, and this is the equation 2. Now substitute, so put 2 in 1. So what do we get? Sigma is nq mu n plus Ni square by N q mu p. Okay, now so we use the concept of maxima and minima. So for finding out the maximas and minima, we take the derivative, and if the second derivative comes out to be negative, the minima exists there. The maxima exists there. If it comes to be positive, the minima exists there. Okay, so taking the first derivative, so d sigma we are differentiating it with respect to electron concentration. So we get Q mu n minus Ni square by n square Q mu p. Understood? So now solve it. We take the another derivative, d square sigma by dn square. It is plus 2 Ni square by n cube Q mu p. So what does this signify? Ni square will always be positive, n cannot be negative, so n cube cannot be negative, it's always a positive value. Q for holes is positive, mu p cannot be negative, so this is always positive. The minima exists. Okay, so the minimum conductivity of the semiconductor can be obtained by making this first derivative equating the first derivative to 0. So now it's clear that at certain concentrations the conductivity of a semiconductor will be minimum, because the second derivative is already coming out to be positive. Okay, so for minimum conductivity we equate d sigma by dn to 0. Okay, so we get Q mu n minus Ni square by n square Q mu p equal to 0. So Q cancel ho gaye. So when you solve, you get n as Ni square root of mu p by mu n. So we get the electron concentration. This is very much important. Okay, so we get this particular relationship. Okay, so this represents the concentration of electrons when the conductivity of a semiconductor is minimum. And similarly, you can find out the whole concentration. We can put this equation in the mass section law formula. So put above in 2. So we get the whole concentration, if we solve, as Ni square root of mu n by mu p. This is also important. These two relationships are very important to keep in mind. So we can use these concentrations to find out the minimum conductivity. So let's put these two in put above two expressions in 1. Okay, so we get sigma minimum as Ni square root mu p by mu n Q mu n plus Ni square root of mu n by mu p Q mu p. So sigma minimum comes out to be Niq 2Niq square root of mu n mu p. So this expression is important. Okay, so this expression is applicable to both p-type and n-type semiconductors. Even if you take had you considered the semiconductor as p-type semiconductor by default, it would have resulted into the same expression. So this is what you will get at the very end of the derivation. Okay, so now let's have some more concepts linked to this. So let me use another pen so that it makes it more clear to you to understand. Now we can find out the expressions for the donor impurity concentration or acceptor impurity concentration. So using electrical neutrality equation or the law of electrical neutrality, Nd plus P is equal to Na plus N. So by default we are considering Na is equal to 0 because n-type semiconductor. This will be equal to 0. So we get Nd is equal to n minus p. So Nd comes out to be Ni square root of mu p by mu n minus square root of mu n by mu p. But wait, this is the expression, this is the expression that we will get at the end for Nd. But you must be thinking that mobility of the holes, since mobility of the holes is less than the mobility of electrons, so Nd expression, the value of Nd will be negative. This thing is negative. Alas, how is this possible? Nd cannot be negative, the concentration cannot be negative, but this expression is resulting into something that we cannot even expect from the expression to result into. So this is what is resulting into a negative expression, but this is not true. So there must be some theory behind it that we shall discuss. For the time being, you should remember this particular expression into your mind. Now let's do it for p-type semiconductor. So for p-type semiconductor, you have Nd equal to 0, so we can say that P is equal to Na plus N. So we can get Na as P minus N and Na as Ni square root of mu n by mu p minus square root of mu p by mu n, which is a positive value. So this expression is good. This is resulting into something that we can expect it to result into. Okay, now let's do the analysis. Let's do the analysis of these two expressions. Okay, so for n-type semiconductor, let's use another pen. It is important to note down that minimum conductivity occurs at T is equal to 400 Kelvin. Okay, it's important. Now above this conductivity, what happens, that's we are going to discuss. Since n is equal to Ni square root of mu p by mu n, and we know that mu p is less than mu n, and if mu p is less than mu n, your n will be less than p. But for n-type semiconductor, p is greater than n. Okay, so from here, since mu p is less than mu n, your n will be less than Ni, which is not true, and p will be greater than Ni, and Nd is negative. So this cannot be positive. So hence for temperatures greater than or equal to 400 Kelvin, n-type semiconductors start to act as p-type semiconductors. Understood? This is very much important. Minimum conductivity occurs at 400 Kelvin, and beyond this temperature, your n-type semiconductors start acting as p-type semiconductor. This is very much important. Okay, but there is no effect on the p-type semiconductor. P-type will remain p-type. Okay, so it's better. So it's better to operate semiconductor below 400 Kelvin. Okay, minimum conductivity occurs at 400 Kelvin. Okay, so let's now have a look at the second case, which is for the p-type semiconductor. Okay, so what happens when sigma is minimum? So this is when sigma minimum. Okay, P will be equal to Ni square root of mu n by mu p. We know that mu n is greater than mu p. So this implies that p will be greater than ni and n will be less than ni. Okay, understood? And your na is a positive value, so this is satisfying, so there is no effect. So when temperature is greater than 400 Kelvin, p type semiconductor will remain as is. Okay, no change in the characteristic, but it is advisable to operate the semiconductors below 400 Kelvin temperature. Okay, so they are very important concept, and you can expect a hell lot of theoretical questions in a GATE examination or any other PSU examination or in IES examination. So it's better to know these concepts very well versed with these concepts. Okay, now we are starting with the yet another very important topic of discussion. Okay, this is important in so we are going to discuss about equation for concentration of electrons in the conduction band of intrinsic semiconductor. Okay, so we are now starting with this concentration. What is the effect of the concentration of, what is the equation for? Okay, so we know when we increase the temperature, the the covalent bonds are broken in the semiconductor, and the electrons become free electrons, and they start jumping from the valence band to the conduction band, leaving the holes in the valence band. So we can say that the energy of the holes is confined in the valence band, and the free electrons energy is confined in the conduction band. Okay, so we know that this is the band diagram of conduction. This is the conduction band, this is the valence band. Okay, the free electrons exist here at the temperatures greater than the absolute temperature, so and the holes exist here. Okay, so we can say that this is basically your EC and this is basically your EV. Okay, so we can say that EC is the minimum energy level of conduction band, and EV is the maximum energy level of valence band. And we can say that free electrons have energy in the range and holes okay minus Fa2 EV. So the equation for the concentration of electrons in the conduction band is N is equal to Nc e to the power minus EC minus EF upon kT. We will derive this equation later, so this is important. Okay, Nc is equals to N is equals to Nc e to the power minus EC minus EF upon kT. Okay, where EF is the Fermi energy level and your NC is basically the material constant. It does depend on temperature. Where your NC is 2 into 2 pi k bar T mn upon h square to the power of 3 by 2. Okay, where k bar is in basically joules per Kelvin. Okay, k bar is Boltzmann constant. K bar is Boltzmann constant, which is joules per Kelvin, in joules per Kelvin, where K bar is 1.38 into 10 power minus 23 joules per Kelvin, not in electron volts. Keep in mind that. Okay. So from here we can see that NC is proportional to T to the power 3 by 2. So this means that NC is temperature dependent, and H is a Planck's constant, 6.626 into 10 power minus 34 joules second. Okay. So this is very much important. So N is equals to NC e to the power minus EC minus EF upon KT. Understood? So where, and one more term you must have seen in the expression, that it's Mn. Mn is basically the effective mass of electron. It's effective mass of electron. Okay, and this changes with the material. Okay, it changes with the material. It is not like a rest mass of electron which is fixed, which is 9.1 into 10 power minus 31 kg. So it depends on the material. It changes with the material. Okay. For example, for silicon, your Mn is 1.08 into M. M is basically the rest mass of electron, where M is rest mass of electron, which is equal to 9.1 into 10 power minus 31 kg. So we can calculate for Mn for silicon. Mn is 1.08 into 9.1 into 10 power minus 31. This comes out to be 9.828 into 10 to the power minus 31 kg. Okay. So this is the effective mass of an electron in a silicon. Understood? And now the next one is the equation of concentration of holes in valence band of intrinsic semiconductor. Okay, understood? So let's have a look at that. So the energy of holes, as discussed earlier, resides between minus infinity to minus infinity and EV. So holes energy belongs to minus infinity to EV because they are always present in the valence band. And the whole concentration formula is P is equal to NV e to the power minus EF minus EV upon KT. This expression is also important. Okay, where NV is material constant. Okay, and your NV is 2 into 2 pi K bar T MP upon H square to the power of 3 by 2. Again, MP is the effective mass of a hole. Hole is basically has a positive mass. It just represents the absence of electron with a charge opposite to that of an electron. So NV also depends on temperature. Okay, MP is effective mass of hole, which is again material dependent. For example, for silicon, let's just take the example of silicon. For silicon, your MP is 0.56 of M. Mass of the hole will be equal to the mass of the electron, which is 9.1 into 10 to the minus 31 kgs. Okay, m is the rest mass of electron. Mass will of the whole, and this will remain the same. So mp 0.56 into 9.1 into 10 power minus 31, and this results into 5.096 into 10 to the power minus 31 kg. Okay, I would like you to make a note here that for silicon and germanium, your Nc is greater than Nv, as Mn is greater than Mp. But for gallium arsenide, Nc is less than Nv, as Mp is less than, as Mn is less than Mp. Okay, and if Mn is equal to Mp, your Nc is basically equal to Nv. So this is basically the assumption. This is not practically possible, but this is just an assumption. So I would like you to note some points to remember. Okay, let me mention here that hole has a positive mass, has mass equal to that of an electron, and charge of equal magnitude to that of an electron, but with opposite sign. Holes are more closer to nucleus than electrons, so are confined, or you can say bounded strongly with the attractive forces with the nucleus, than the electrons. So mu p is less than mu n. Okay, understood? Now let's move further. So expression of intrinsic carrier concentration derivation. This is the derivation. Okay, now let's derive the expression of intrinsic carrier concentration using the concepts that we have learned so far. So for intrinsic semiconductor, electron concentration is given by Nc e to the power minus Ec minus Ef upon kT, and hole concentration is Nv e to the power minus Ef minus Ev upon kT. Okay, this is 1 and this is 2. So we know that Ni square is Np. So we know this for any semiconductor, Ni square is basically Np. So Ni square, if we just multiply 1 and 2, we get Nc Nv e to the power minus Ec plus Ef minus Ef plus Ev, okay, upon kT. So we get Ni square is NC NV minus of EC minus EF minus of so in this case minus EC minus EC minus EV is EG. So this is EG naught upon KT. So this is basically EG upon KT is the energy band gap. EC minus EF is energy band gap. So this Ni square is equal to EG upon minus of this is e to the power EG upon KT. This is the third expression. This is Ni square. Now we know that NC is 2 into 2 pi k bar T Mn h square to the power 3 by 2 and MP and your NV as 2 into 2 pi k bar T MP upon h square upon 3 by 2. Plug these values in, you get NC NV as 4 into 2 pi k bar upon h square cube Mn MP to the power of 3 by 2 T cube. Okay, so let this whole thing as, let us take this thing as A naught. Okay, so from here we get NC NV as A naught T cube, because this is a constant value. 2 pi is constant, k bar is constant, h square is constant, Mn and MP are constant for that particular material that we are using. So if we plug these values in, in the Ni square expression, so we get, so Ni square is equal to A naught T cube e to the power minus Eg naught upon KT, and Ni is equal to, is basically equal to square root of A naught T to the power 3 by 2 e to the power minus Eg naught upon 2 KT. Okay, understood. So we can say that Ni is proportional to T to the power 3 by 2. It depends on the temperature. So as your Ni increases, as your temperature increases, your Ni increases. Okay, so let's quickly go through the basic definition of Fermi energy level, when we shall discuss greatly about it in the succeeding lectures. So what is a Fermi energy level? There are two ways that you can define. One way I am defining it in this topic. So EF is basically measured in electron volts, and Fermi energy level is the maximum energy level at 0 Kelvin. So how can we define it? We can define it as the maximum energy possessed by an electron at 0 Kelvin, at absolute temperature at 0 Kelvin. So maximum energy, or you can say, is the maximum kinetic energy of an electron at 0 Kelvin. So we can say that Fermi energy level is half m V max square. Okay, and from here we can find out the maximum velocity of an electron. It is nothing but 2 EF by m meters per second. Okay, so for now this is enough. So I'm basically okay. So let me give you some 3 homework questions that you must should try. So these are the 2 questions which you should try as a homework, and I will give you the answers to these questions in the next lecture. So just read the questions carefully, note down what's the important point which is important points mentioned in the question. So then solve the question. Okay, that's it. Thank you very much.